So now we have the concept of an arbitrary collection of sets, and union and intersection etc. can be defined for such arbitrary collections. And of course many of the properties we proved for the union or intersection of two sets etc. can be generalized to this context also. And sometimes we may be using special kinds of notation for collections of sets. For example, if you are having a finite collection of sets, we may denote it by A1, A2, A3 etc. A. Each set is indexed by a positive number. This is notation. That is, here each this is actually a collection of sets, but we are writing this collection of by using the index, and the indices used are 1, 2, 3 etc. up to a particular number. In this case, the union is usually denoted by union I is equal to 1 to n of ai, rather than A1 union, A2 union etc. union an. Usually that is abbreviated as union I is equal to 1 to n of. And sometimes we may have a sequence of sets. What is a sequence? Z plus is the set of all positive integers. Z plus denotes the set of all positive integers, that is 1, 2, 3, 4 etc. Now a sequence in a set X is a function from Z plus 2 X. This is a formal definition of a sequence. That is, for a sequence, there will be, sequence is a function from set of positive integers to X. So for every positive integer there will be an image in X. The image of 1 is usually denoted by X of 1. Image of 2 is denoted by X of 2. Image of 3 is denoted by X of 3, etc. Image of n is denoted by X of n, etc. etc. So if X is a sequence, for every positive integer 1, 2, 3 etc., there will be an image in X. So there will be in X1, X2 etc. This X1 is called the first term of the sequence, X2 is called the second term of the sequence, X of 3 is called the third term of the sequence, etc. etc. Some people, instead of writing X of 1, some people write as X sub 1, subscript 1, or for if the X of n is a positive integer, is denoted by X. That is the nth term of the sequence. And sometimes we may even, instead of we write x1, x2, x3 etc. That is the x1, x2, x3, these elements are written with commas, and here is 3 dots, and then we put symbol brackets. This is usually the notation used for X sometimes. So this is a sequence, and of course we are familiar with various sequences, say 1, 2, 3, 4, 5 etc. The sequence 1 by 2, 1 by 3, 1 by 4 etc. We can various. So this is a sequence. We can find various sequences. sequences of numbers, sequences of, you can consider sequence of any of the elements. And in sequences, these elements need not be distinct. Sometimes the same elements can be repeated. For example, we can have a sequence like 1, -1, 1, -1, 1, -1, etc. So all elements need not be distinct. So this is the concept of a sequence. And there is this concept of a finite sequence also. You take a positive integer n and you take the set 1, 2, 3 up to n. And if you take a function from this set to any set x, such a function is called a finite sequence. So just if you say sequence, that means an infinite sequence. But if it is a finite sequence, you should say finite sequence itself. So if you say just sequence, that means infinite sequence. So finite sequence is a function from this set to x. So then you will be having the function x1 image of 1, x2 image of 2, etc. image of n. And sometimes it is written as x subscript 1, x subscript 2, etc. x subscript 2. And sometimes x is denoted in this fashion, x1, x2, etc. xn. And sometimes we may even write x1, x2, etc. xn without any symbol brackets or comma notation. And this is usually a convention in the case of finite sequences of symbols. I define if sigma is an alphabet, there is a finite set of symbols. I define sigma star as the collection of all finite sequences of elements of sigma, and a language was defined as a subset of sigma star. The elements of sigma star are usually called the strings, and these strings are nothing but finite sequences of elements of sigma. In such context, the finite sequences are written like this rather than this fashion. We can even consider sequences or finite sequences of sets. So what will be a finite sequence of sets? Sorry, or a sequence of sets? I mean infinite sequence. That is, if you have a collection containing a1, a2, etc., an, etc., etc. You may have a collection like this. That is, for each positive integer there is a set. So that is a function from the set of positive integers to this collection of sets. So this can be treated as a sequence of sets. But of course, a set of sets and a sequence of sets are different. Why? In a set of sets, there is no order between the sets. But in the case of a sequence of sets, there is an order. There is a first set, there is a second set, there is a third set, etc. etc. So a sequence of sets is actually is not a set, something more than that. There is a structure in it, there is an order. So sometimes we will be having sequences of sets, like A1, A2, etc. This is a sequence of sets.
The itself a sequence.
What?
A set itself a sequence.
A set need not be a sequence, because in a set there will be several elements, and between these elements there is no structure, there is no relation. You cannot say which is the first element, which is the last element.
Set of integers.
Set of integers, when we say it, the set of integers, we are not implying any order. But when we say the sequence 1, 2, 3, 4, etc., we are implying an order. So a sequence is different from a set. So in sequence, there is a, or in a finite sequence, there is an implied order in that. That is a structured set. Whereas a set contains no structure. A set contains a lot of elements, but we cannot say which element is the first one or which element is the second one. There is no structure in a set. So that is the idea. മനസ്സിലല്ലേ? ഈ ഒരു സെറ്റിലെ എലമെൻറ്റുകൾ എഴുതുമ്പോൾ നമ്മൾ ഏത് ക്രമത്തിൽ എഴുതണമെന്ന് യാതൊരു റൂളില്ല. എങ്ങനെ വേണമെങ്കിൽ പറയാം. ഇപ്പോൾ എ ബി എന്ന് പറഞ്ഞ സെറ്റും ബി എ എന്ന് പറയുന്ന സെറ്റും ഒന്ന് തന്നെയാണ്. എ ബി സി എന്ന് പറയുന്ന സെറ്റും ബി എ സി എന്ന് പറയുന്ന സെറ്റും സി ബി എ എന്ന് പറയുന്ന സെറ്റും എല്ലാം ഒന്ന് തന്നെയാണ്. കാരണം അവിടെ ഓരോ ഓർഡറും പ്രശ്നമില്ല. മറിച്ച് ഫൈനൈറ്റ് സീക്വൻസ് ഒക്കെ പറയുമ്പോൾ നമ്മൾ എന്തുകൊണ്ട് അവിടെ ഒരു ഓർഡറും കൂടി വരുന്നത്. ഒരു സീക്വൻസിലാകുമ്പോൾ ഒരു ഫസ്റ്റ് വേണം, സെക്കൻഡ് വേണം, തേർഡ് വേണം, ഫോർത്ത് വേണം, എക്സെട്ര വേണം. ഫൈനൈറ്റ് സീക്വൻസ് ആണെങ്കിലും ഫസ്റ്റ് സെക്കൻഡ് തേർഡ് അങ്ങനെ nth വരെ വേണം. അപ്പോൾ അവിടെ ഒരു സ്ട്രക്ചർ ഉണ്ട്. അതുകൊണ്ടാണ് നമ്മൾ സീക്വൻസിനെയും ഫൈനൈറ്റ് സീക്വൻസിനെയൊക്കെ നമ്മൾ എങ്ങനെ ഡിഫൈൻ ചെയ്ത്? ദേ ആർ ഡിഫൈൻ നോട്ട് ആസ് എ സെറ്റ് ബട്ട് ആസ് എ ഫംഗ്ഷൻ. എ ഫംഗ്ഷൻ ഫ്രം എ സീക്വൻസ് ഈസ് ഡിഫൈൻഡ് ആസ് എ ഫംഗ്ഷൻ ഫ്രം ദ സെറ്റ് ഓഫ് പോസിറ്റീവ് ഇൻറ്റിജേഴ്സ് ടു എ സെറ്റ്. അപ്പോൾ അവിടെ ഒന്നിനൊരു ഇമേജ് ഉണ്ടാവും, രണ്ടിന് ഇമേജ് ഉണ്ടാവും, മൂന്നിന് ഇമേജ് ഉണ്ടാവും, എക്സെട്ര. എല്ലാ പോസിറ്റീവ് ഇൻറ്റിജറിനും ഒരു ഇമേജ് ഉണ്ടാവും എന്ന് പറഞ്ഞ അർത്ഥം എന്താ? ദിർ ഇസ് എ സ്ട്രക്ചർ. ഒരു ഫസ്റ്റ് എലമെൻ്റ് ഉണ്ടാവും, സെക്കൻഡ് എലമെൻ്റ് ഉണ്ടാവും. സോ സീക്വൻസ് ആൻഡ് set are different. String is, in a string also, a string is actually a finite sequence of some symbols. There is embedded a structure. There is an order. There is a first symbol, there is a second symbol, there is a third symbol, etc. There is an order. So there is so in a set there is no structure. Now, if you are given such a sequence of sets, we can define the union. How will you? In this case, we denote the union as union A n. N varies from 1 to infinity. This is the notation. Rather than A1 union A2 union A3, etc. union An. Instead of writing like this, you can write this. Or sometimes you will be writing like this also. That is An, where n is so this union of a sequence of sets we can write in this way, or even this way. But sometimes our collection of sets need not be countable. It can be uncountable infinite set. So we may not be able to, all infinite set we cannot write as a sequence. For example, you cannot write all real numbers in a sequence. If you write any sequence of real numbers, we can find a real number outside that, because the set of all real numbers is uncountable. So sometimes we may be, so here we are using positive integers to index the set. Sometimes we may be using other sets also. So you can say something like this. Suppose C is a collection of sets. C is a collection of sets. And suppose that I is a set. And consider a function from I to C is a collection of sets and I is a set and F is a function from I to C. Suppose this is a situation. Now, for every element I of I, we are having an F of I, and F of I will be an element of C. We may even have that this function is a surjection. That is, every element of C is an image of some element of I. In that case, instead of writing this f of I, we can also use the notation, the f of I may be denoted by a subscript I, where I is any element of I. And all elements of this collection can be written in this form. And in that case, we use this notation for writing the collection. This is called an indexed family of indexed collection of sets. Indexed collection of sets. Here I am not specifying whether the index set I is finite, countable or uncountable. I don't know. Can be anything. So I is arbitrary. It can be finite in some days, it can be countable infinite some days, it can even be uncountable infinite. I am not giving any specification. So I is very arbitrary. So sometimes we may be using this notation to write a collection of sets. Such an index family can also be defined as a function from the indexing set to this collection and on to function. And corresponding to every I in I, there is a set AI in C. And every set in C is actually the image of some element of I. And this I can be called the index set. And this may be, this is an indexed collection of sets. Sometimes we will be having this notation. And this notation is convenient sometimes. And for if you take such a collection of sets indexed by I, you take the union as this is nothing but the union of the collection of all I elements of I. But this notation is convenient sometimes. Similarly, you can define induction, the intersection also. Of course, when I is non-empty. When I is empty, there will be problem. Unless you are having a universal set or a master set, the empty intersection is not defined. So sometimes, this can be considered as a notational device. There is given a collection of sets. Sometimes instead of writing the various elements, we are writing it in an indexed form. That is, we consider a function from some indexing set onto this family of sets, and for each I in the indexing set, the corresponding image is denoted by a subscript I, and in that case union and the intersection is usually denoted by this symbol. In this case, I can be any set: empty, non-empty, finite, infinite, countable, uncountable. Such collections are usually called arbitrary collections. Arbitrary means we are not specifying any condition. That is, we are not saying whether it is empty or non-empty. We are not saying whether it is finite or infinite. We are not saying whether it is countable or uncountable. Arbitrary means can be anything. So we can even define the union and intersection of an arbitrary collection of sets, possibly indexed by some. And some of the properties we proved for union and intersection of two sets can be generalized to this context also. For example, we have this De Morgan law. Suppose AI, an element of I, is an arbitrary collection of sets. Then you take union and take the complement of that. This will be nothing but the intersection of AI complement, that is complement of A union is the intersection of the complements, and intersection complement of the intersection will be the union of the complements. Complement of a union is the intersection of the complements, and complement of the intersection is the union of the complements. You will be having De Morgan laws like that, and proof is not difficult. But of course, in this case, you should make sure that I is non-empty. Otherwise, this intersection is not defined. And how to prove these things? Proof is easy. That is, X is an element of union I is an element of I, AI complement. If and only if X is not an element of union A, and X is not an element of the union means X is not an element of AI for every I. This happens if and only if X is an element of AI complement for every element, and this happens if and only if X is an element of AI complement for every I means X is an element of intersection AI complement. So we get this. Similarly, you can. So De Morgan law is true whether your collection of sets is contain 2 elements, 3 elements, finite number of elements, countable number of elements, or even uncountable numbers. So this arbitrary result can be written in this way using the index, arbitrary indexing set I. Discrete mathematics പിന്നെ അൺകൗണ്ടബിൾ സെറ്റ്സ് അധികം വരില്ല. പക്ഷേ ഈ മാത്തമാറ്റിക്സിൽ പലപ്പോഴും നമുക്ക് വരുന്ന പല കളക്ഷൻസും അൺകൗണ്ടബിൾ കളക്ഷൻസ് ആയിരിക്കും. അപ്പോൾ അൺകൗണ്ടബിൾ കളക്ഷൻ ആണെങ്കിൽ അതിന് സീക്വൻസ് ആയിട്ട് എഴുതാൻ പറ്റില്ല. അപ്പോൾ അതിന് ഇൻഡെക്സ് ചെയ്യാൻ വേണ്ടിയിട്ട് എന്തെങ്കിലും ഒരു പ്രത്യേക സെറ്റ് ഉപയോഗിക്കുന്നത് സൗകര്യമായിരിക്കും. അപ്പോൾ ഇതൊരു നമുക്ക് ഒരു നൊട്ടേഷണൽ സൗകര്യമായിട്ട് വിചാരിച്ചാൽ മതി. You can, if you don't like to use this index notation, you can also write it like this. If C is a collection of sets, you can write union C for the, of course, C. Let me take a non-empty collection. Then you take the union C, and if you can write the complement of that is the complement of a union is the intersection of the complements. So that will be intersection of all complements A belongs to script C. And you take intersection C, the complement of that will be the union of the complements. Union of the complements will be so De Morgan laws for the arbitrary collection can be written in this way also, if you don't like to use this index notation. In the for the function, I said union image of a union is the union of the images. That can also be stated for an arbitrary collection. If the collection, if you take an arbitrary collection of subsets of a set X, if is a function from X to I, and if I element of I is an arbitrary collection of subsets of X, then f of union AI is equal to union f of AI. The image of a union is the union of the images. This is true for an arbitrary collection of subsets. But for in the case of intersection, we know that the result is not true. In the case of pre-images, also we have this result, that is f inverse of union is the union of the f inverses. And For inverses, we are having the result for the intersection also. There is f inverse of intersection AI is the intersection of f inverse AI. Preimage of an intersection is the intersection of the preimages. This result is true for arbitrary also. Sometimes we may be using. This concept of bijection or 1-1-1-2 function is very important. One importance is that for sets A and B, there exists a bijection to sets for finite sets A and B. There is a bijection f from A to B if and only if A and B contain the same number of elements. This is one importance of bijection. If A and B are sets and if there is a bijection between A and B, there is a 1-1-1-2 map or 1-1 corresponds. This exists if and only if the number of elements of A is equal to number of elements of B. In the case of finite sets, this is a very important property of bijections. And a bijection of one set to itself is sometimes called a permutation. Suppose A is a set. A bijection from A to itself is called a permutation. So how many bijections will be there from a finite set A with n elements to itself? A is a finite set. How many bijections will be there from A to A? Suppose A is a finite set with say n elements, say x1, x2, etc., xn. Now, any bijection will take x1 to one of these elements. So, x1 can go to x1, x2, x3, etc., xn. How many ways that can be done? That can be done in n ways. Now, once x1 is mapped, what about x2? Then x2 can be mapped to any of the other elements. x1 is mapped to one element. Our bijection cannot take two elements to the same element. So, x2 can be mapped to any element other than the element to which x1 is mapped. So, how many possibilities are there? n minus 1. And what about x3? So, now x1 and x2 are mapped. Two elements are already taken. They cannot be used. So, that x3 can be mapped to any of the other elements. That is any of the n minus 3 elements. And that can be done in n minus 2 ways, sorry, n minus 2 ways. And then, so and etc. etc. X1, by the time x1, x2, x3, xn minus 1 are mapped, all elements except the last one, except one will be taken. So we will be forced to map xn to then. So then the last xn can be mapped only in one way. So how many ways, how many bijections are there from this set to itself? There will be n into n minus 1 into n minus 2 etc. into 1, or 1 into 2 into 3 into up to n. What is that? That number is usually denoted by n factorial. So the number of bijections of a set X with n elements is n factorial. So what is 1 factorial? By number of bijections from a singleton set itself. There is only one. So that is equal to 1. What about 0 factorial? The set of all bijections of the number of bijections of the empty set to itself. From empty set to empty set, that a function will be a subset of phi cross phi. And what is phi cross phi? Phi. And phi cross phi, phi is having only one subset. And so there is only one relation from empty set to itself. And that relation, we observe that that is a function. In fact, that is a one-one function. You cannot prove that it is not a one-one function, because if you want to prove that it is not a one-one function, you have to show two elements in the empty set which are mapped to the same element. That is impossible. So you cannot prove that it is not 1-1, therefore it is 1-1. You cannot also prove that it is not onto. Why? If you want to prove that it is not onto, you will have to show an element in the empty set to which no element is mapped. You cannot show such an element. Therefore, you cannot prove that it is not onto. Therefore, you will have to admit that it is 1-1 also. Is onto also. So empty function is a 1-1 and onto function. So there is exactly one function from empty function to from empty set to empty set, which is both 1-1 and onto. There is bijection. So you can even take 0 factorial as 1. That is usually taken. But sometimes people say you take 0 factorial as 1. Defined. It's defined as without an expression. But this can be given as an expression. So number of bijections of the empty set is equal to 1. So 0 factorial can be taken as 1.